Welcome to this coding problem walkthrough. Today, we'll be exploring problem number 2079, titled Watering Plants. This problem challenges us to think critically about simulating processes and optimizing resource usage. Let's dive in and understand how we can solve it step by step. In this problem, you have a row of plants that need to be watered. The plants are represented as an array of integers, where each element indicates how much water a particular plant requires. You have a watering can with a specific capacity, which starts full. You begin at the leftmost plant and move sequentially to water each one. If your watering can runs out of water before fully watering a plant, you must walk back to the river to refill it, then return to the plant to continue. Walking either to the next plant or back to the river counts as 1 unit of distance. The goal is to calculate the total distance you need to walk in order to water all the plants. The input includes the plant's array and the capacity of the watering can, and the output is the total distance walked. Let's look at an example. Suppose the input is plants equals 2, 4, 5, 1, 2, and capacity equals 6. Here's how this scenario plays out step by step. You start with a full watering can, which has a capacity of 6. First, you water plant 0, which needs 2 units of water. This leaves you with 4 units of water. You then walk one step to plant 1, water it, and it uses the remaining 4 units. At this point, your watering can is empty, so you need to return to the river to refill. This requires walking 2 steps back to the river and 2 steps to return to plant 2. You water plant 2, which needs 5 units, leaving just 1 unit in the can. After this, you move to plant 3 and use the remaining water to fully satisfy its need of 1 unit. After watering plant 3, your watering can is empty again, so you walk 4 steps back to the river to refill and then 4 steps to return to plant 4. Plant 4 needs 2 units of water, which leaves you with 4 units in the can. Finally, you add up all the steps: 1 step for plant 0, 1 step for plant 1, 2 steps to the river and 2 back for plant 2, 1 step to move to plant 3, and 4 steps to the river and 4 back for plant 4, plus the 1 step to water it. The total distance is 17 steps. This gives us the output of 17. Now, let's consider another example where plants equals 1, 1, 1, 4, 2, 3, and capacity equals 4. Starting with a full watering can, you water the first 3 plants, which require 1 unit each, leaving you with 1 unit of water. After watering the 3rd plant, you don't have enough water for the 4th plant, which needs 4 units. You walk 3 steps back to the river, refill your can, and return 3 steps to plant 4. After watering plant 4, you have no water left, so you walk 4 steps to the river and 4 steps back to plant 5. Plant 5 needs 3 units, so you repeat the process. When you sum up all the steps, the total distance comes out to 14. Finally, consider the case where plants equals 7, 7, 7, 7, 7, and capacity equals 8. Starting with a full watering can, you water plant 0, which requires 7 units, leaving you with 1 unit. You then move to plant 1, but since it also requires 7 units, you don't have enough water. You walk 1 step back to the river to refill and return 1 step to plant 1. This process repeats for plants 2, 3, and 4, with each requiring a refill. Each refill involves walking back to the river and returning, creating a repetitive pattern. Adding up all the steps results in a total distance of 49. The constraints ensure the problem is solvable for up to 1,000 plants, and edge cases include scenarios like having only 1 plant or needing frequent refills. By considering these cases, you can ensure your solution is both efficient and robust. To start, let's think about the simplest way to tackle this problem, the brute force approach. The intuition here is straightforward. Imagine walking along the row of plants with a watering can. For each plant, you check if there's enough water left in your can to water it. If there is, you water the plant, reduce the remaining water in your can by the amount the plant needs, and move to the next one. But if the water in your can isn't enough, you need to walk back to the river, refill your can, and then return to the current plant to continue. Throughout this process, we count every step you take, whether it's moving forward, going back to the river, or returning to the plant. The key observations here are that you need to track both the amount of water left in the can and your position along the row of plants. Additionally, every time you refill, you add extra steps for the trip to the river and back. Importantly, since you're processing the plants in order, you can solve this using just one traversal of the array, making the time complexity O(n). The space complexity is O(1), since we don't need any additional data structures. While this approach is efficient in terms of complexity, we can also think about optimizing the implementation to make it cleaner and more concise, though this won't reduce the computational cost significantly. Now, let's focus on the strategy we've chosen to solve this problem, and optimize simulated walk using a greedy approach. The idea is to directly simulate the process of watering the plants while keeping a running count of the steps. You start at the river with a full watering can and iterate through the plants one by one. For each plant, you first check if the remaining water in the can is sufficient to water it. If it is, you simply water the plant, deduct the required amount from your can, and increment your step count to account for moving forward. However, if the water isn't enough, you calculate the steps needed to return to the river, refill the can, and come back to the plant. These steps are added to your total. Once the watering can is refilled, you handle the current plant and then proceed to the next. This process continues until all plants are watered. We chose this strategy because it's both efficient and intuitive. It avoids unnecessary complexity by focusing directly on the essential operations, making the implementation straightforward and easy to debug. Comparing this to the brute force approach, both share the same O(n) time complexity and O(1) space complexity, but this optimized greedy method has cleaner logic and is more maintainable. The key insight, or the aha moment, in solving this problem comes from realizing that the task can be broken down into 3 clear steps: checking the remaining capacity of the watering can, refilling when necessary, and counting the steps taken. By focusing on these discrete actions, the problem simplifies into a linear traversal with constant space usage. This clarity makes the greedy approach feel natural, as it mirrors the actual process of walking back and forth to water the plants while tracking steps. This realization not only streamlines the implementation but also highlights the elegance of the solution, combining efficiency with simplicity. In this problem, we are tasked with watering a series of plants arranged in a straight line. Each plant requires a specific amount of water, represented by an array plants, where the ith element indicates the water required by the ith plant. We use a watering can with a fixed capacity, which decreases as we water each plant. If the water in the can becomes insufficient to water the next plant, we must return to the river, refill the can to its full capacity, and then continue. Each movement, whether it's to the next plant or to the river and back, counts as a step. The objective is to determine the total number of steps required to water all the plants. To solve this, we start by initializing 2 variables, steps, which will keep track of the total movements, and remaining_water, which represents the current amount of water left in the can, initially set to the given capacity. The algorithm proceeds by iterating through the plant's array. For each plant, we first check if there is enough water in the can to water it. If the remaining_water is greater than or equal to the water required by the current plant, we simply water the plant, reduce the remaining_water by the required amount, and increment the steps by 1 since we move to the next plant. However, if the remaining_water is less than the water needed, we have to return to the river to refill the can. This requires us to calculate the round-trip distance to the river and back, which is 2*i steps, where I is the index of the current plant. After refilling, we water the plant, adjust the remaining_water, and add 1 step for the final movement to the plant. Additionally, there are edge cases to consider, such as if the array contains only 1 plant, where the steps would simply be 1 as long as the can's capacity is sufficient, or if the capacity is smaller than the largest water requirement, which would make the problem unsolvable. Analyzing the algorithm's complexity, we see that the time complexity is O(n), where n is the number of plants. This is because we iterate through the array exactly once, performing constant time calculations for each plant. The space complexity is O(1), since we only use a few variables, such as steps and remaining_water, to manage our calculations. The algorithm employs a greedy approach, refilling the can only when absolutely necessary, which ensures an optimal solution. This strategy is possible because the problem constrains movement to either forward progression or resetting to the start, simplifying the calculation of steps. By dynamically tracking the remaining_water, we avoid redundant calculations and maintain efficiency. The primary data structure used is the plant's array, which stores the water requirements, while variables like steps and remaining_water manage the state of the computation. To understand the algorithm in action, let's consider an example where plants equals 2, 4, 5, 1, 2, and capacity equals 6. We start at plant 0 with the can full at 6 units. The first plant requires 2 units of water, so we water it, leaving remaining_water at 4, and incrementing steps to 1. Moving to plant 1, we find it needs 4 units, which matches our remaining_water. After watering, remaining_water becomes 0, and steps increases to 2. At plant 2, which needs 5 units, we don't have enough water. We return to the river, adding 2*2 equals 4 steps, refill the can, and then water the plant. After this, remaining_water is 1, and steps has increased to 7. Finally, we move to plant 3, which requires 1 unit. We water it, reducing remaining_water to 0 and bringing steps to 8. At plant 4, which requires 2 units of water, we again find that remaining_water is insufficient. This requires a trip back to the river, adding 2*4 equals 8 steps. After refilling the can, we water plant 4, leaving remaining_water at 4, and the total steps becomes 17. The final output for this example is 17 steps. To optimize, we can check if the capacity is greater than or equal to the sum of all water requirements. In such cases, the result is simply the number of plants, as we can water them in one pass. Edge cases include scenarios with a single plant, where the steps equal 1 if the can's capacity is sufficient, or situations where the can's capacity is less than the maximum plant requirement, making the problem invalid. If the array is empty, the result is 0, as no steps are needed. This Python code solves the LeetCode problem 2079, watering plants. It calculates the total number of steps needed to water all the plants, given the limited capacity of a watering can. Here's a detailed explanation of the implementation. 1. The watering plants function takes 2 inputs, plants, a list where each element represents the water requirement for a plant, and capacity, which is the maximum water the can hold. 2. The variable total_steps is initialized to 0. It will track the total number of steps taken to water all the plants. Additionally, current_water is set to capacity, representing the water available in the can initially. 3. The function iterates over the plants list using a for loop. The index I represents the current plant's position, while plants I gives the water requirement of the plant. For inside the loop, the function checks if the current plant's water requirement, plants I, is less than or equal to the water remaining in the can, current_water. If sufficient water is available, the plant is watered, and the number of steps is incremented by 1 to account for moving to the next plant. The current_water is then reduced by plants I. 5. If the water in the can is insufficient to water the current plant, the function calculates the steps required to return to the river, refill the can, and come back to the plant. This is done by adding I*2 plus 1 to total_steps. I*2 accounts for going back to the river and returning to the plant. Plus 1 accounts for watering the current plant. The current_water is then set to capacity plants I to reflect the water used to water the plant after refilling. 6. After the loop completes, total_steps contains the total number of steps taken to water all the plants, and the function returns this value. This implementation ensures that the problem's requirements are met efficiently. The time complexity is O(n), where n is the number of plants, as it processes each plant exactly once. The space complexity is O(1), since the algorithm uses only a fixed amount of extra space. This is the Java implementation of the watering plants problem, LeetCode number 2079. The logic mirrors the provided Python solution, with adjustments for Java syntax and conventions such as type declarations and array handling. The method iterates through the plant's array, tracking steps required to water each plant. If the current water capacity is insufficient, it simulates a refill trip back to the river before continuing. The solution uses clear variable naming and adheres to Java's concise class structure. To begin solving this problem, we start with an example where the plant's array is 2, 4, 5, 1, 2, and the watering can has a capacity of 6. Initially, we set total_steps to 0, and current_water is equal to the full capacity, which is 6. Starting at plant 0, which requires 2 units of water, we check if the current water is sufficient. Since 2 is less than or equal to 6, we water the plant directly, reducing current_water to 4. We then move to the next plant, incrementing total_steps to 1. At plant 1, which requires 4 units of water, the current water is just enough. We water the plant, reducing current_water to 0, and move forward, increasing total_steps to 2. This sets us up for the next part of the process as we continue watering the plants. When we reach plant 2, which requires 5 units of water, the current_water is 0, which is insufficient. This means we need to return to the river to refill. Since the plant index is 2, the round trip to the river takes 4 steps. After refilling, we return to the plant, adding 1 extra step to water it, for a total of 5 steps. After watering, current_water decreases to 1, and total_steps becomes 7. Moving to plant 3, which requires 1 unit of water, we find that the current water is sufficient. We water the plant, reducing current_water to 0, and move forward, bringing total_steps to 8. Finally, at plant 4, which requires 2 units of water, we don't have enough water, so we return to the river. Since the plant index is 4, the round trip takes 8 steps. After refilling, we return to the plant, adding 1 extra step to water it, for a total of 9 steps. This leaves us with current_water at 4 and total_steps at 17. The final output for this example is total_steps equal to 17. Moving to another example, let's consider plants 1, 1, 1, 1 with a capacity of 2. At the start, we initialize total_steps to 0 and current_water to 2. For plant 0, which requires 1 unit, the water is sufficient. We water the plant, reducing current_water to 1, and move forward, increasing total_steps to 1. Next, we reach plant 1, which also requires 1 unit. Again, the water is sufficient, so we water the plant, reducing current_water to 0, and move forward, bringing total_steps to 2. At plant 2, which requires 1 unit of water, the current_water is 0, so we need to return to the river. The plant index is 2, so the round trip takes 4 steps. After refilling, we return to the plant and water it, adding 5 steps in total. This reduces current_water to 1 and increases total_steps to 7. Finally, we move to plant 3, which requires 1 unit of water. The current water is sufficient, so we water the plant, reducing current_water to 0 and increasing total_steps to 8. The final output for this example is total_steps equal to 8. Lastly, consider plants 7, 7, 7 with a capacity of 7. Starting at plant 0, we find that the plant requires 7 units of water, which matches the capacity. We water the plant, reducing current_water to 0, and move forward, bringing total_steps to 1. At plant 1, the water is insufficient, so we return to the river. As the plant index is 1, the round trip takes 2 steps. After refilling, we water the plant, adding 1 step, for a total of 3 steps. This brings total_steps to 4. Finally, at plant 2, we again need to return to the river. Since the plant index is 2, the round trip takes 4 steps. After refilling, we water the plant, adding 1 step, for a total of 5 steps. The final total_steps is 9. To analyze the time complexity of this solution, let's break it down step by step. The algorithm iterates through the plant's array exactly once. For each plant, it performs one of 2 operations. The first operation is watering the plant and moving to the next one. This involves subtracting the plant's water requirement from the current water supply, which is a constant time operation, or O1. Additionally, it increments the total steps counter, which is also O1. The second operation occurs when the current water supply is insufficient. In this case, the algorithm calculates the steps required to return to the river, refill, and come back to the plant. This calculation, along with updating the water supply, is still an O1 operation. Since each plant is processed exactly once, the outer loop runs O(n) times, where n is the number of plants. As all operations inside the loop are O(1), the total time complexity of the algorithm is O(n), which is the product of the O(n) loop and the O(1) operations within it. The absence of nested loops or recursive calls ensures that the time complexity is solely determined by the single pass through the plant's array. Now, turning to space complexity, the solution uses only a constant amount of extra space regardless of the input size. Specifically, it uses variables like total_steps and current_water, both of which require O(1) space. The algorithm does not create any additional data structures that depend on the size of the plant's array. Since no extra memory is allocated based on the size of the input, the space complexity is O(1). This fixed memory usage makes the algorithm highly space efficient. When analyzing the best, average, and worst-case scenarios, the time complexity remains O(n) in all cases. This is because the algorithm always makes a single pass through the plant's array, processing each plant exactly once. In the best-case scenario, all plants can be watered without needing to refill the watering can. Even then, the algorithm still iterates through the array once, leading to O(n) time. In the worst-case scenario, the algorithm has to refill the watering can after watering each plant. Even in this case, the loop still processes each plant once, resulting in O(n) time. The average case, where water requirements are distributed more evenly, also leads to O(n) time since the loop's behavior doesn't vary with the distribution of the water requirements. Regardless of the scenario, the time complexity is consistently O(n). Comparing this optimized solution to a brute force approach highlights its efficiency. A naive approach might simulate each step individually, recalculating positions or revisiting plants unnecessarily. This could result in a time complexity of O(n², as redundant calculations for each plant would quickly add up. In contrast, the optimized solution directly computes the required steps for each plant in O(n) time, avoiding unnecessary recalculations and improving performance significantly. Mathematically, the big O of O(n) is justified because the algorithm processes each plant exactly once, and each operation within the loop is O(1). The absence of nested loops, recursion, or data structures that grow with input size solidifies the space complexity at O(1), ensuring efficient memory usage. This combination of O(n) time and O(1) space complexity makes the solution both fast and space efficient. When solving the watering plants problem, there are a few common mistakes to watch out for. First, failing to reset the water can capacity properly after a refill is a frequent error. If you forget to reset the capacity, it will lead to incorrect distance calculations or incomplete watering of plants. The fix is simple: always make sure to reset the capacity to its maximum after each refill. Another issue is skipping edge cases. For example, consider scenarios where there's only one plant in the array or when all plants require the same amount of water. Overlooking these can result in index out-of-bounds errors or incorrect outputs. To avoid this, explicitly test for edge cases during development. Finally, inefficient refills can also be problematic. Some solutions refill the can even when there's enough water to handle the current plant, which unnecessarily increases the distance covered. The solution here is to carefully check whether a refill is truly needed before taking action. Another mistake to avoid is overcomplicating your solution. Some approaches use nested loops or additional data structures, which can increase time complexity significantly. For example, what should be an O(n) solution might end up as O(n² instead. The best way to tackle this is by sticking to a single pass through the array and using minimal variables to track your state. Similarly, ignoring the problem's constraints can lead to major issues. If you assume that the water can's capacity or the plant's water requirements are unbounded, your solution might produce incorrect results or even runtime errors. To prevent this, always read and interpret the constraints carefully, ensuring your solution adheres to them. By keeping these points in mind, you can develop a cleaner and more efficient solution. From an interview perspective, recognizing the pattern in this problem is key. It's essentially a variation of the greedy strategy, where you need to make optimal decisions at each step, like when to refill the water can. Interviewers often expect you to explain why your solution runs in O(n) time, so be prepared to break down how you achieve this level of efficiency. Additionally, handling edge cases is critical. Be ready to discuss scenarios like having only one plant, a water can with less capacity than the smallest plant requires, or situations where all plants need the same amount of water. Communication is also vital. Clearly articulate your thought process, especially when deciding when refills are necessary. Make sure to highlight trade-offs between different approaches, such as brute force versus an optimized solution. These skills will help you stand out during interviews. This problem also shares similarities with other classic LeetCode problems. For instance, in LeetCode 55, Jump Game, you use a similar greedy approach to decide at each step whether you can proceed further. LeetCode 134, Gas Station, involves managing resources, like gas, to determine if you can complete a circuit, again focusing on optimization. In LeetCode 1021, Remove Outermost Parentheses, you must carefully track state using counters for open and close parentheses. Finally, LeetCode 409, Longest Palindrome, while in a different domain, still emphasizes efficient counting and state management. By practicing these related problems, you can strengthen your understanding of the patterns and techniques involved, making it easier to solve similar challenges. There are also alternative approaches to solving the watering plants problem. The brute force method involves simulating the entire process step by step, checking each plant and refilling whenever necessary. While easy to implement, it's highly inefficient, with a time complexity of n squared for larger inputs. A more optimal solution is the greedy approach, where you track the remaining water and only refill when absolutely necessary. This minimizes the total distance walked and ensures an n time complexity. However, it does require careful implementation to avoid common pitfalls. Another potential strategy is the two-pointer technique, which simulates the watering process from both ends of the array. While this can be useful for variations of the problem, it might complicate the implementation unnecessarily for this specific scenario. Each approach has its trade-offs, so understanding their strengths and weaknesses is essential for choosing the right one in different contexts. Great job making it to the end. Today, we tackled problem number 2079, watering plants, by exploring a brute force approach and breaking down the problem step by step. Remember to practice simulation-based problems to strengthen your problem-solving skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!